This lecture we are going to see something about adsorption. So why we are studying this one? I was thinking to deliver my lectures on chromatography, but I think it's better to talk a bit about the working principles of adsorption, because whatever that we are going to learn in column chromatography, you will not understand a thing if you don't know what adsorption is all about. Yeah. So I will cover this topic maybe in one lecture or possibly more than one, and then we will move on to chromatography. For this module, we are going to just cover only the liquid chromatography. We are not going to touch gas chromatography. Liquid chromatography is most widely used in many pharmaceutical industries, mostly for purification and also for separation of different components from a solution mixture. So that's what we are going to study. So for this lecture, what I am going to talk is like I will define what adsorption is all about, and you must know that one, like adsorption is an unit operation and it's widely used in many pharmaceutical industries, also any chemical industries. Adsorption will be like one of the final steps in the product purification. Sometimes it will be even used like something we call it as a polishing step. Yeah, so if you need to remove something, or like for example wastewater treatment, if you want to remove some pollutants, then we will go for adsorption. Or in pharmaceutical industries, it's widely used mostly to purify proteins, or some fermentation products. If you want to remove some particular product from the fermentation broth, then, and if they are specific to some adsorbent materials which we are going to study now, so then we can go for this technique. And also many people like this technique because you don't need to give some massive external force. For example, if you perform a chemical reaction, you need to perform agitation. So for that you have to spend some amount of power to stir your impeller, and that causes additional cost on the final product. Yeah? So which means you're going to spend some money in manufacturing something. But many people like adsorption, especially liquid phase adsorption, because something that it happened naturally, especially if you're going to purify something, especially in continuous mode, then adsorption is very good technique. It won't even need that external force for this process to happen. So that's what we are going to study. I just put some words like where it is widely used. So it's mostly used in purification of proteins. And another good thing about adsorption is, like, imagine if you have a protein dissolved in your fermentation broth, and if you want to remove it, we can't go for other techniques. For example, we can even heat the solvent and take the product out. But imagine if your protein is sensitive to some temperature, or it will get denatured, so it will lose its original structure, so it won't do the job anymore of the protein. So sometimes it's necessary to retain the structure of protein. So in that case, adsorption becomes really handy, and they are in fact many industries still rely on adsorption techniques to purify proteins. So this is one main advantage. And then more recently I see like many people are producing different type of acids using fermentation technique, because it's so cheaper to produce. And adsorption seems to be a very good technique to remove acids both at lab scale and also at industrial scale. So I read a lot of papers, especially in the last few years. They are using different type of adsorbents to remove acids from fermentation broth, and there are many good advantages. As I said, it works well at room temperature, so which means you don't even need to give an you don't have to spend some money in maintaining some specific temperature. Only then your process will move forward. It's not true. Adsorption is very spontaneous process. If you give the enough driving force required for this process to happen, then it will happen naturally. So this is one of the advantage of adsorption. I'm going bit faster this topic because I know some of you might have learned this adsorption technique probably in physical chemistry, and chemical engineers might have even studied this in some other module. So what we are going to cover is, like, we will just cover the working principles. You should know some of those knowledge in order to move to the next topic of a column chromatography. So we will cover only those parts. So whatever the knowledge that you are going to acquire through studying adsorption now, that you are going to gain some extra bit of understanding when we are going to talk about column chromatography. Yeah. So, and then other advantages, like it can be used as a purification technique, or to recover some products, and then without altering the product quality. So this is something I already talked about, especially when it comes to protein. Imagine if you use some other technique, if you are trying to purify something, and if it's going to change the structure of your protein, which means you modified or altered the structure of your desired product. So this won't happen with adsorption. Yeah, so adsorption will selectively go and take your protein or absorb your protein, and then it will also retain the structure of your protein. So that's one of the key advantages of adsorption. And then this is another big advantages. So I put the word perfect. So what does that mean? Like even if you were if you're going to deal with some solution with extremely low concentration, say for example, say like even a pharmaceutical compound dissolved in a liquid, say if it is at very trace amounts, very low concentration, obviously we cannot create a supersaturation out of that liquid. So what to do with that one? So and you cannot say like you have only 0.1 gram of pharmaceutical compound in say like 2 liters. If you want to evaporate all the solvent to recover that few grams of your pharmaceutical compound, again it's going to be very laborious process. So those type of during those times we can use adsorption technique. Adsorption technique works so perfect, especially when your solute concentration is very low. Yeah, so this is one big advantages of adsorption. And in fact many industries go for adsorption only when they are going to deal if with like say they want to purify something or recover something, and they are only in very low concent they're present in some solution but in low concentration. Then the first unit operation they will prefer or think about is adsorption technique. So this is something you should know. And then this is something related to chromatography. I added one word like just to follow the pen, which I'm drawing a box, something like a separation of molecules. Say like imagine you have 3 compounds A, B and C. They are exactly similar. Maybe in B there might be one hydroxyl group might be missing, maybe in C some methyl group may be missing. Apart from that all the structure look exactly same. Then adsorption technique will become very handy. It can specifically target one compound at a so this is something very good with adsorption. And we will stick to these principles of adsorption, especially when it comes to separation of molecules, that we will cover a bit more detail when we are going to talk about column chromatography. Yeah? So I hope you all understand what is structurally similar molecules. I can draw something quickly. Maybe imagine you have 3 molecules like that. The only difference is in the third molecule you have one methyl group, in the second molecule you have one hydroxyl group. So something like that. So adsorption can separate even these type of compounds which are almost structurally identical, although some tiny difference that you can notice at molecular level. So adsorption can do this job. And also adsorption is preferred over extraction or crystallization, especially when the concentration is very low. If you have to remove say like 0.1 milligrams per liter of some compound, so why do we go for crystallization? Obviously no matter, even if you go to cryogenic temperature, you cannot create a supersaturation, so obviously you cannot rely on crystallization. And also if you take extraction, to remove the tiny bit of some compound, you need to add a massive amount of solvent, and who knows, maybe you will never attain a two-phase region. So there are few disadvantages with these two techniques. So in that time you can go for adsorption. Adsorption works very good, especially when you are dealing with some system that where your solute concentration is extremely low. So I know you all know what is solution, what is solute, what is solvent, and even know I'm 100% sure you all know what is adsorption. You must have studied in analytical chemistry and also in probably in some other module, yeah, physical chemistry. Yep. So that's why I'm going a bit faster, just assuming that you know already, you know some terminologies involved in adsorption. So why we are learning about adsorption? So we should know how adsorption works, or the working principles to understand column chromatography. And then you should know what is the driving force required for adsorption to happen. Yeah, so this thing you should know. Only if you know what's the driving force required for adsorption, only then we can talk something in the column or in chromatography lectures. Yeah, and then so how to define an adsorption? So this is my definition. So adsorption, if you want, we can define as like a selective transfer of a solute from a bulk solution to the surface of a solid material. Yeah, so imagine if you have some 1 liter of some solution where you have a tiny bit of your solute. Say for example they are protein molecules and they are present in very low concentration, say 0.1 grams per liter. And what we do is like we add some adsorbent. So this is some solid material, we call this as adsorbent. We add inside. So once they come inside, your solute molecules will stick onto that surface of the adsorbent. So which means your solute molecules are transferring from your solution side to your solid side. So you can filter the solution. If you filter it, you will get a clear solution, and in the bottom you will get adsorbent with your products recovered. They will be on the surface of your adsorbent. So that's how adsorption works, and adsorption works really good, especially when you're dealing with very low concentration. Even if you have a very small concentration difference, yeah, like so still you can move your solute from here to here, from the solution side to the solid side. So and why this is happening? So why your solute molecules are moving from the solution side to the adsorbent side? That's because we have a concentration gradient. Yeah, so that's the only driving force that you need. So concentration gradient, so this is the only driving force you need. In your solution you have 0.1 grams per liter, while your adsorbent contains 0 grams per liter. So there is a concentration difference of 0.1 grams per liter. So naturally your molecules will move from higher concentration zone to lower concentration zone. So that's how the physics work on in this world. So that's the only driving force you need, and adsorption will happen even if the driving force is very less. Even if you have 1 grams per liter in the solution or 0.1 grams per liter in the solution, irrespective of the driving force, adsorption works really cool. So that's the thing you should know about. And then normally the solid material that we use to take the solute from the solution is called adsorbent, and the solute which is moving from the solution side to the solid side, that we call them as a solute, or we call them as adsorbate. So these are some terminologies: adsorbent, adsorbate, adsorbent, and so on. And then always stick to this. Let me check. So pay attention to this one. Yeah. So whenever I call this word, where is that? Couldn't find. Surface of the solid material. Yeah, so adsorption is a surface phenomena. So whenever I talk about adsorption, you should think it is a surface phenomena. Yeah, so it's what does that mean by surface phenomena? Like if you put your solid adsorbent, so they will come only and stick to the surface of the adsorbent. They will not enter to the bulk of your material. Like so you all know what is absorption. Yeah, so if you put a sponge in water, sponge can take the water inside. So something like the water fill the whole bulk of your sponge material. Yeah, so we call them as absorption, and adsorption is something different. It goes only to the surface of the material, and it will not enter to the interior of the solid structure. So that's the meaning of adsorption. I hope you all understand it. Probably you might have studied it as well before in some other modules. Also, I'm going to say how we are going to perform, or how we will perform, an adsorption experiment in the lab. Normally it's one of the easiest experiment to perform in the lab. All you need is some set of like a conical flask or a small vial, and something to stir your solution, and few analytical equipments to analyze what's the concentration of your solute in the solution before and after adsorption. So adsorption is extremely simple, and believe it or not, it's the same way they perform it in the industry as well. So whatever, if you know how to perform an adsorption experiment in the lab, you are going to repeat the same procedure in a larger unit in industries. So it's so straightforward, it's very very simple. Yeah. So what happens, I don't know what I wrote, what happens. Oh yeah, what happens when adsorption is happening? Yeah, so what really happens once you added an adsorbent into the solution? So you take a solution, say our job, it contains a lot of protein, and say like this is like a, say, or maybe even for example, okay, just to stick to some protein, say we have like 2 liter and we have only very few grams of protein, say 0.2 grams, which means the concentration will be 0.2 grams per liter, and we need to recover this protein from the solution. So we add some adsorbent material. Let's change some color. So let's call these blue ones as adsorbents. So solute will move from the solution side to your adsorbent side. So that's what really happens. So we have a concentration gradient once you added your adsorbent. So your adsorbent are free of your solute molecules. So solute molecules will move from the solution side and go to the surface of your adsorbent, and we call this, or we can call it as some mass transfer is happening. So transfer of some solute mass from the solution side to the surface of your solid adsorbent, and this happens, we call this process as, well, diffusion. So diffusion happens only if there is some concentration gradient. Yeah, so try to remember these terminologies: mass transfer, so because some mass is transferring from one side to another side, and that process we call it as diffusion, and this diffusion process is driven by something we call it as a concentration gradient. So I hope you all remember or understand up to this point. And then in this process, whatever is happening now so far, there is no chemical reaction. We are just pushing some molecule from the liquid phase or from the solution to the solid side of your adsorbent. So practically no new bond formation, practically no bond breakage. So that's not a bad news. In fact, that is a very good news, because especially if you break some bond or if you create some bond, which means you are going to rupture the structure of your material. For example, protein, if you create some new bond, probably it's going to change the structure of your protein, and nobody likes that. Yeah? So everything is physical process, no chemical reaction. So to keep that in the mind, and then this mass transfer will happen even if we do not provide or does not provide any external force. So what does that mean? Like if we talk about crystallization, something like, okay, forget the crystallization part. What I mean is like you have some solution with protein, and if you add adsorbent, even if you don't provide like agitation, or if you don't provide some constant temp, like some external energy, so that to maintain some level of temperature inside the reactor, if you just have that concentration gradient, diffusion will proceed immediately, and then your solute will start to move from the solution side to the adsorbent side. Obviously the speed will vary. If you want to speed up this process, then you have to spend some energy by providing agitation and so on. But even if you don't do that, this mass transfer process is going to happen, and that's because you have that beautiful concentration gradient. All these concepts are like so elementary level, very basics, but you need, if you understand this concept, then whatever that we are going to talk in chromatography, that will become extremely simple. Yeah, so let's move on to the next one. Okay, and this mass transfer process, just look at, maybe you can change it to highlighter. So this mass transfer process will happen due to a phenomena called bulk diffusion, and I said to you there is a concentration gradient, and then solute moves from one side to other side of your material, and I call it as there is some diffusion is happening. And to be precise, in chemical engineering we call this process as bulk diffusion. Bulk diffusion refers to some terminology where your solute particles are moving from the bulk of your solution. Yeah, so in this reactor, so whatever the solution we have, we call it as a bulk solution. So solute molecules move from the bulk of your solution to the surface of your solid adsorbent. So if I ask in objective type questions, what is a bulk diffusion, you should know how to deal with that. Okay, in chemical engineering we call this as mass transfer, because something is driven by something is driven by concentration gradient. And then just to remember this, these are some physics that you should remember. So the driving force for mass transfer is just concentration gradient. And then, so how fast? I said to you it happens naturally, but if you want you can speed up the movement of solute molecules from your solution side to the adsorbent side. And even so, and how fast it moves, it depends on your concentration gradient. So the rate of mass transfer, or rate of how fast your solute move from your solution side to the adsorbent side, that just depends on your concentration gradient. Yeah, so I hope you all understand up to this point. So what do I mean by this is, like, imagine you have two experiments. So one solution you have 0.1 grams per liter, another solution you have 2 grams per liter, and you put exactly say like 1 gram of adsorbent in both of these experiments. So the solute molecules will move very slowly from the solution side to the adsorbent side, whereas in the second experiment solute molecules will move very fast from your solution side to the adsorbent side. And that's happening because you start with a very high concentration gradient in the second experiment. In the second experiment, your concentration gradient between this concentration gradient, how we are defining, like the difference between the solute concentration in the solution to the solute concentration in the adsorbent. So that's what I'm calling as concentration gradient, and that you start with 2 grams per liter in the second experiment, which means your mass transfer is going to be extremely fast. So that's the thing that you should remember, and there is a name for this simple law, like mass transfer rate proportional to your concentration gradient. It's called Fick's first law of diffusion. So it's called the Fick's law. It's proposed by Fick. And then there are something I already said, like adsorption works when you have working at a higher concentration, like here, like 2 grams per liter, and it will work even if you start from a very low concentration, say like a 0.1 grams per liter, for example. And then adsorption will work even if we go to an extreme case scenario. Just look at here. So imagine if you have your solution, you have only one molecule of your solute, and if you add an adsorbent, still you can push your solute from the solution side to the adsorbent side, possibly. Yeah, it depends. So adsorption will work even for, like, even if your solution is extremely dilute. Yeah, like especially this type of solution where we have only one molecule in the solution, we call this type of this type of system as like infinite dilution. So we cannot dilute the system more than this. Yeah, so the maximum dilution that you can get is like one molecule in some solution. Yeah, so that's the maximum dilution, or some people they call it as infinite dilution. So even for that extreme case, adsorption will work. So keep those things in your mind. And then we are just going to talk a bit about that adsorbent material that we are going to add to remove something from the solution. So I just put something like let's do some paper pen experiment. So we have some solution which is shown here, where we have a lot of solute molecules completely dissolved into the solution. So if you put a light, the light will come to the other side, which means completely dissolved, everything is transparent, no turbidity inside the solution. So the light molecules will pass through the solution. Yeah, so it's completely transparent. Then we are going to add an adsorbent, and then, as I said, your solute molecules is going to move from your solution side to the surface of the adsorbent. So I so far I showed some simple diagram, like your none of your your material adsorbent material is going to look like this like a small spherical ball. Yeah, it's going to it may be powder, it may be crystalline, no matter whatever. But these materials, whenever I say like a surface, it's not like you are throwing some ball and that ball have some surface and everything that's going to come and stick to the surface, like something like an external surface of the object. No, it's not. So whenever we are talking about adsorption, whenever we are talking about the surface in the adsorbent, we are talking something else. So it's not the external surface, it's the surface that makes the pores in those material. So whatever the material that we are going to use it as adsorbent, they are mostly porous and they have enormous amount of surface area. So what do I mean by, okay, whenever I say pores mean like this material contains a lot of pores. And if you want, we can calculate that porosity, like imagine, say, like if you have a cube like that. So if you know the size, the length of the cube, from that we can get the volume. And if imagine if this cube contains a lot of pores, and if we know what's the volume of the pore in that cube, then we can get some rough number on the porosity of this cubic material. Yeah, so just put it only to talk about what's porosity is about. Just come back to this topic. This is something you should remember. Whatever the material adsorbent that we commonly use in industries or in lab, they are really porous, and some of these materials have a porosity of 90%. So 90% is like pushing the porosity to the limit of the material. 90% porosity, just imagine, like you think you have a big solid material, but that solid material contains nothing, just pores. Only 10% make the structure, and the remaining 90% they are porous. So that's the typically we in industries they select materials that has a porosity ranging from 10 to 90%, and typically the price of the adsorbent is roughly correlated to the porosity of your material. Yeah, so if it's 10%, probably it's less. If it's 90% porous, the price is going to be higher, and that's because people use different type of synthesis protocols in order to create that level of porosity. And for that you have to spend a lot of energy, a lot of time, different complex techniques, maybe more than one step to produce the material with 90% porosity, whereas you need only one step, a simple step that you can make at room temperature to make a material with 10% porosity. So the price varies depending on the properties of your material, and the properties of the material depends on the sophistication of the technique that you use in order to produce that material. In this case, whenever I talk about material, it refers to the adsorbent. I'm not going into many details because I know probably I'm still not sure whether you know all the principles of adsorption or not. So whenever I talk about porosity, so what do I mean by that? Imagine this is like a chunk of your particle. If you put under a microscope, you will see something like that in scanning electron microscope. So just assume this is your spherical your adsorbent material. Say your activated carbon typically look like this under, if you put it under a microscope, like a very powerful microscope. And then so everything is, so whatever, I can draw it black. So whatever I am filling, so those are your solid material, yeah, solid structure. Sometimes it's not a bad idea to use PowerPoint. So just assume this blue are the surface, and then that surface have some porosity. This white, let me change the color. So these holes which I'm using now in highlighter, they are like pores. So this is what I mean by porosity. Yeah, porosity. And then I said to you before, like whenever we are dealing with adsorption, something is moving from solution to the surface. So to the surface, it means like it doesn't mean that it's going to stick to this surface, not the external surface of your solid adsorbent. Whenever I talk about surface, just assume that green color, the one which I'm going to green color ink, they are your solid molecules, say they are your protein. So protein will go and stick to the surface of the pores, something like here, which I'm drawing now. So if this is your pores, they will go into the pores. So this is the, and whatever the boundary that makes the pores, that's called your adsorbent surface. Just to look at this one. So I hope you all understand. Yeah, so you have some adsorbent material that contains a lot of pores. So obviously pores will be bounded by some surface, and that's the place, or that's the spot where your solute molecules will transfer or from your solution side, and they will go and get adsorbed onto the surface which is bounding your pores in your adsorbent material. Yeah. So whatever I showed in the left hand side, so this part of your diagram, maybe use a highlighter. So this is we can call it as a highly porous because it contains lots of pores, and this is some example for a less porous material. It has only small porosity, one here, another one here. So follow the highlighter. So these pores will host your protein molecules or any other solute molecules. Yeah, so these are your pores. I'm just writing in green color. Just follow the ink. So I hope you all understand up to this point. I'm sure you all learned about what is an activated carbon. This is one of the most widely used adsorbent in industry. And what is meant by activated carbon? So why don't we call it as carbon? So whenever we call it as activated carbon, so the word activated, that corresponds to microporosity. Activated, it doesn't mean like there is something activation happening on. So we are calling, we can call it something like we are creating micropores. So if your carbon contains micropores, we can call it as activated carbons. If your carbon doesn't contain micropores, you just call it as like a piece of carbon. Yeah, so that's the thing you should remember in your mind. So, and this type of pores should actively adsorb small gas molecules. Just remember, in our this model, we are just going to talk about liquid phase adsorption. But since we are talking about activated carbon, what does that mean? What does microporosity mean? So that's why I have to use this word or just introduce about something relevant to gas adsorption. Yeah. So what does this micropores mean? So this micropores. If you have a micropores, which mean they can actively adsorb smaller gas molecules. Yeah, so smaller gas molecules, they're so tiny. For example, their molecular diameter will be only less than a nanometer, like 0.364 nanometer, and this is nothing but the diameter of your nitrogen gas molecule. Yeah, so activated carbons are carbons that contains pores that can host or that contains pores typically in this range 0.364 nanometer to very larger sized pores, say like 2 nanometer or more than 2 nanometer. Some material might even contain 50 nanometer or even more than that. Yeah, so we don't have to go into those details like what is micropore, what is mesopore, what is macropore. You don't have to go into those details for this module. Okay, if you want, I can say it quickly, like so anything less than 2 nanometer are micropores, and 2 to 50 nanometer we call it as mesopore. Anything greater than 50 nanometer we call them as macropores. So these are the something try to remember in your mind. And then just a reminder again, for this module we are dealing with liquid phase adsorption. I'm sorry that I wrote already in the notebook, because every time when I write and when I talk, it's taking extra time while recording the videos. That's why I thought better write what I want to say and then just start to record the videos. Yeah, so this way I can save say like 20 minutes of my time, and also you can also learn extra things in less amount of time. And few more things you should remember, like adsorbents can be crystalline, it can be amorphous. Activated carbon is an amorphous material. Yeah? And then there are some crystalline materials, some are like silica based and more like zeolites, and more recently there are more sophisticated material, we call them as metal organic frameworks. So we don't have to go into those details, but just to remember, so adsorbents, there is no rule like it should be crystalline, it should be amorphous. There is no rule like that. If any of your material contains this, if they are porous material, if they contains enormous surface, and if those surface can host your target molecule, it can be protein or an acid or any like for example antibiotic, or even some simple API compound like paracetamol for example, then you can use them as your adsorbent material. So just to remember those things in mind. And many materials can do the same job. Silica can do the same job, activated carbon can do the same job, zeolites can do the can do the can do the same job, but other clay based materials, they all can do the same job. Yeah, so these are some things you should remember. And there are many polymeric materials, people are using them as adsorbents. So all of them can if they contains the right level of porosity, right level of surface, obviously they can adsorb your solute molecules from the solution side to the surface. And industries at the moment, the most frequently used materials are activated carbons, and also like mostly silica based materials. And the main reason is like they're they're very stable to moisture. Yeah, so even if you add it in the water, the structure will remain same. If you put a crystalline material, it might dissolve. Imagine if your water act like a solvent, then your crystals will dissolve. So it's nobody likes that. Or your and crystals are so vulnerable to temperature. If you want to remove something at bit higher temperature, you might lose the properties of your adsorbent, you will lose your crystallinity and so on. So at the moment industries use activated carbon and silica based materials. They both are highly stable to water and also to temperature. So keep those things in the mind. I might ask in some objective type questions in the exam. And then okay, let's come back to the topic of adsorption. Always remember this word, mass transfer is the key for adsorption. So if you don't have mass transfer, so if you don't have concentration gradient, there is no mass transfer. Yeah. So for adsorption is happening because there is some mass is transferring from your solution side to the solid side. And then okay, and also I just a reminder, this is, I said to you, this is a purely a physical process, and which means there is no bond breakage. And obviously there is you can do the adsorption with something we call it as a chemisoption. There you might encounter with some bond formation, but we are not going to cover this topic. Yeah, so in this particular module, so we are learning adsorption. And in pharmaceutical industries, mostly they deal with the physical adsorption process because they don't work at very high temperatures, and because it's going to affect, it's going to kill your product quality. So they will work at mild operating conditions, and and mostly they stick to physical adsorption technique. If it's a chemical adsorption, you are going to lose your product quality, and nobody likes it. So in this module we are not going to cover something about chemisoption, but if you are really interested, obviously you can do some literature search, or you can read some books to know more about it. Yeah, you might find more information in any physical chemistry textbook. So why I talk about a purely physical process, because we are going to talk about what type of forces are involved while you are dealing with the adsorption. So whenever I say physical process, we call it as a physisorption. That's the technical term for that. And this is mostly governed by something we call it as a van der Waals, or we can call it as a London dispersion forces. So keep those things in this mind. So you should know what type of forces are involved when we are going to talk about physical adsorption, because if you know this one, then when you are studying chromatography, our life will become bit easier. So so what is this force? What do I mean by van der Waals or London dispersion force? Yeah. Let's change to pen. I'm 100% sure you all must have studied even in your school time, like Rutherford Bohr atom model. So you have some nucleus cloud here, which is mostly positively charged, and then you have your electrons that revolves around your nucleus. So this is your electrons. So these two guys, they think electrons are something like a particles, like in your planetary system. So and they revolve around the nucleus, something like these are your planets, and this is nucleus is something like your sun. So this is what they thought, and this is the model proposed by them. So something like your electrons will revolve around your nucleus. So that's what they thought, which is correct. But the only thing is they assume these are like particles, like some piece of ball moving around your nucleus. But in fact electron doesn't work like a particle. So imagine if this is your nucleus, imagine you have only one electron on this side. I'm just writing it here. So it won't move in this only one particular, it's not going to go like this, like in a circular orbit. It's not true. They will move randomly around something like around the nucleus, and we call this the the path where the electron can randomly take and move, something we call it as an electron cloud. So what does this electron cloud will tell us about? So this electron cloud is something like any point on that electron cloud, we it is highly probable that we can find electron at any one of those part within that electron cloud. So I hope I managed to say it correctly. So what does that mean? Like electron cloud, like at one instant at time you can find electron here. Just change the color, follow the blue line. So at one instant we can find the electron here, another 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 instant we can find the electron here. So something, that's what the cloud is about. So the probability, it's more probability that we can find electron at maybe any one of those locations within that cloud. Yeah. So that's how it works. And this model was actually proposed by a Nobel Prize winning physicist, Erwin Schrödinger. I don't have to talk about these topics in this lecture, but I just put it because this guy is an Irish scientist. Yeah, he's an Austrian Irish scientist. Probably you might have known him. Yeah, so he thought that electrons don't behave like a particle but like a waves. Yeah, so they can move randomly within its own space inside that electron cloud. So that's the thing you should know. So why we are talking about this? Because we are going to talk something about van der Waals interactions or London dispersion forces. So I made some diagram here. So we have this nucleus in the center, then we have this electron, and we have some cloud. So we can find electron here, randomly at different time intervals. Yeah, so it's going to be inside this cloud. So this is a spherical cloud. I try to draw it like a 2D image, but if you want, you can just put it in the Google like electron cloud. You will see those 3D images. And this electron will move randomly, one time here, another time in the left side, another time in the top, another time in the left. So what happens is like, imagine if this is a nucleus, and this time your electron is here, on this side of the cloud. So electron is negative charged, so this side will become negative, and since electron moved to the other side, this time will become positive. So this is one say just one atom, and you imagine there is another atom here, and in this case your electrons are on the other side of your atom, and so this side will become negative and the other side will become positive. So they can interact with each other because they are opposite charge, they can attract each other. So this type of forces, so molecules coming together due to this type of forces, we call them as van der Waals forces, or we call them as London dispersion forces. So whenever we talk about a physical adsorption, they are extremely weak, and is driven by forces, or the forces involved in physical adsorption is very weak. And imagine like your molecules are randomly fluctuating, your electrons, sorry, so which mean you can, so which mean the forces associated with them are extremely weak. Even if you give some extra bit of energy, you can put these particles apart. Yeah, if you increase for example the temperature of your system, then they will start to repel each other and these molecules will go apart. So that's the meaning of what type of forces involved in adsorption. So why we are studying this one van der Waals forces or interaction is, you should remember one thing in your mind, like these are the forces that you need in order to make your adsorption to happen, but these forces are very weak, and we can easily break them, which means if something, say like you have some adsorbent surface, say some positively charged group is here, and then your molecule, one of the, say this is your molecule, say a protein molecule, and say this side you have some negative charge due to the phenomena that we talked. So they will come together and then they will adsorb onto the surface of your adsorbent. This is your adsorbent, let's call this is your protein molecule, and we can break this one. So these forces are extremely weak. Yeah, so even if you pass a fresh solution that doesn't contain your protein molecule, it will knock off this molecule from the surface and then it will go back to the solution. So the forces are extremely weak. So that's the thing you should remember. So which mean, so you can do the exactly the opposite side of your adsorption. So adsorption is moving your solute from the solution to the surface, and then you can move the reverse process, you can make the reverse process to happen. We call it as a desorption. So I just put some how to do that. So you can take a column, you fill your adsorbent material that already contains your protein molecules, and you put some pure solvent which is solute free. Once you pass your pure solvent, it will knock off your solute and then it will come outside. So this time you will get a solvent plus solute. So this will be your solution. So this is something like you are removing the already adsorbed material from the adsorbent side to the solution side. I hope you all get up to this point. So this is not a tough concept. And how we do an adsorption experiment, this is super simple. So I just put a simple experiment here. You take some different vials, say like and this contains 0.1 grams per liter of your or the concentration of your solute is 0.1 grams per liter, and just assume we are doing with 25 ml solution, and then so all these vials contain 25 ml of our solution that contains a solute. So let's take it as a butyric acid. So butyric acid normally they produce in especially in the recent years they started to produce using fermentation. So if you want to remove this butyric acid from the fermentation broth, people use activated carbon as adsorbent. So let's do this experiment like a virtual experiment. So you have different vials. So we add 25 ml, 25 ml, 25 ml in all these vials, and all these vials contain different concentration of your solute material. The first one contains 0.1, second one contains 2 grams per liter, third one contains 5 grams per liter, fourth one contains 10 grams per liter, fifth one contains 20 grams, 30, 40 and 50 grams per liter. So how many experiments we are doing? 1, 2, 3, 4, 5, 6. So we're doing 8 experiments, and then we add 0.5 gram of activated carbon in each of these vials. 0.5 gram. So in all of these vials we are adding 0.5 gram of our material, and then we are going to give complete mixing. For 25 ml we can use a simple magnetic stirrer. For industrial scale reactors, then we have to go for some overhead stirrer. So overhead stirrer something look like this one. I showed it here. So you have an impeller, and then you have some motor in the top that rotates your impeller. So this is how it looks like in a typical industrial scale adsorber. So what we do is, like, once we add our adsorbent material, we agitate, we provide agitation to the solution, and then we agitate using a suitable stirrer. And typically we agitate for 24 hours. Just assume that we add everything, we measured accurately 25 ml in 8 different vials, and each vial contained different concentration of your solution, and then we added 0.5 gram of your adsorbent material in each of those vials, and then we agitate for 24 hours. So why we need 24 hours? This is more than enough to achieve an equilibrium. So I hope you all know what's an equilibrium. And so 24 hours, this is not some universal rule. It can be even 1 hour. So how to know the time required to achieve an equilibrium? Normally we do some trial and error experiment. So what we do is, like, we take only one vial, say like the concentration is 2 grams per liter, and then we add our adsorbent, and then we start to agitate, and then we will put some analytical probe in the top inside your reactor, say like an UV spectrophotometer for example, and then that allows you to monitor the concentration. So during adsorption, your solute will move from solution to the adsorbent surface. So naturally the concentration of your solute in the solution will decrease. So we can monitor from the UV spectrophotometer. So if you look at the profile, it will look something like that. Here I plotted time versus concentration in the solution. Concentration of solute in the solution, in this case butyric acid, or if you are dealing with protein, it will be the concentration of your protein. So it will decrease something like that. So it will continuously decrease, and after some time it will reach to some constant value. So that's the point of equilibrium. So at this point your solute concentration in the solution is in equilibrium with solute concentration on the surface of your adsorbent. So they can coexist. Your solute can exist some on the solution side and also in your adsorbent side. So something they reach to an agreement, we call it as an equilibrium stage. So that's the meaning of this. And say, imagine if this equilibrium is achieved in 1 hour, then if you go back to this experiment, we can finish this experiment at the end of 1 hour plus 1 hour. So normally we do this type of experiment, we provide extra time in order to ensure we reached a complete equilibrium. So this is how we do the experiment in the lab, and this is how they do the process at industrial scale. They will have some fermentation broth or other type of solution that contains some solute, and they will add some adsorbent material, and then they will continuously stir. If you want, we can even put a pad tool like UV spectrophotometer. That's a pad tool. We can put it in the reactor and monitor the concentration. Why not? So I hope you all understand up to this point. And what really happens during adsorption, or you imagine this, I put it like so this is your adsorbent surface that contains a lot of some active sites, we can call them, or so your solute molecules will come and fill the surface, something like that. And once the adsorbent surface are completely filled, so that's the point we call, so it's completely filled, so your adsorption stops. So that's what actually really is happening. So we don't have to worry about when the adsorption stops or other things. So that's a bit more complex topic. Then I have to talk about adsorbent heterogeneity and so on. For the moment, what you think is like you have some surface and solute molecules come and sit on the surface of your adsorbent due to the diffusion process. I call it as a bulk diffusion, and for that to happen we need something called it as a concentration gradient. So once you do this experiment, say like at the end of once you reach to your equilibrium, we can stop the stirring and then we can remove the adsorbent, and then we can check what's the final concentration of your solution in each of these vials. So I just put it here, something like a table. Just imagine we did 8 experiments, say 1 2 3 4 5 6 7 8, and say like we started with what, 0.1 grams per liter, and then 2 grams per liter, 5 10 20 5 10 20 30 40 and 50, I guess. Yes, 50 grams per liter. And then say what will be the final concentration here. So just assume we got some value like here, say like say 0.02, and the second vial the final concentration is 0.3, 2.21, 6.2, 15.3, 25.19, 34.83, 44.27. So these are the values we got. So what we did is like we start with a solution that contains butyric acid, and then we added some mass of your adsorbent. Just assume we added 0.5 grams in each of these vials. So this is your final concentration, or we can call it as a equilibrium concentration, because this is the concentration that exists in the solution, so which is in equilibrium with something which is already adsorbed onto the surface. So if you look into your solution, it will be something like this. So you have your adsorbent, so this is your adsorbent, so this is your solute molecules which are already adsorbed, so adsorbed solute, and you will also have some solute molecules in solution, so they are in equilibrium with each other. So in the second experiment, if you put a probe, if you want to measure the concentration of your solution, it will be say like this is your second experiment, final concentration will be 0.3 grams per liter. And if you want to know what's the concentration of your solute onto the surface, it's very easy. Yeah? So whatever, if you imagine you started your solution from 2 grams per liter, and at equilibrium you reached 0.3 grams per liter. So 2 minus 0.3, that should have moved to the solid side. So that will be equal to 1.7 grams per liter. So this is in terms of per liter. That's the unit. Try to remember that. And then what we need to calculate is the amount adsorbent. If I want to know, and I know I did all this experiment, I didn't perform this experiment with 1 liter of my solution. I did everything with 0.2, like I didn't talk about the liter of the, just assume I said already 25 ml. So we did all this experiment in 25 ml solution. So if I need to calculate how much mass that I moved, like how much mass of solute I moved from the solution side to the solid side, to 1 gram of my solid side. So if you want to calculate, you have to do the mass balance. So how to perform this one? So we have our initial concentration, say like this is, say let's assume we are talking about experiment 2. We started with 2 grams per liter, and we ended up CE will be 0.3 grams per liter. So the difference between this C0 minus CE will be 1.7 grams per liter. This is per liter of solution. And just assume we did the whole experiment only in 25 ml of our solution. So 1.5 grams per liter. So if you multiply by the volume that we used in our experiment, which is 0.025 liters. So liter and liter will get cancelled. So that will give some idea about how many grams of your solute is moved from the solution side to the adsorbent side. So it will tell how many grams. So how many grams we moved. So I'm going to use the next page. C0 is 2 grams per liter, C is 0.3 grams per liter. So C0 minus C should be 1.7 grams per liter of solution, or we can even call it as per liter of solvent. So and we did all experiment with our V is 25 ml, which is equal to 0.025 liters. So if you just multiply C0 minus CE multiplied by V, that should give 1.7 multiplied by 0.025 grams per liter plus gram liter get cancelled. So this will tell whatever the value that we have here. So let's put 0.025. So this is nothing but 0.0425 grams of solute or butyric acid moved to the solid side in this experiment. So and imagine we did our experiment only with 0.5 grams. Our mass of our adsorbent that we loaded into the reactor is only 0.5 gram. So you divide this value by mass of your adsorbent. So that will be equal to 0.0425 divided by mass of the adsorbent, that's 0.5 gram. So that should give some number in terms of, so C0 minus CE V by M, that should give mass of your solute transferred from solution side, or mass of solute transferred per gram of your adsorbent. So this is something like a normalized data, milligrams per gram. So why do we do this one? So why do we normalize by milligram per gram? For example, like how do you call, like if you do an experiment, say in 25 ml, say like you start with 2 grams per liter and then you add 0.5 grams and so on. And if you do the same experiment, say with 50 ml, say 2 grams per liter of concentration, this time we add 0.5 plus 0.5 gram, and you will get a new CE value. But once whatever the CE value you get, if you convert it into milligrams per gram, that value will match with this value that you performed with the 25 ml reactor. Yeah, so this value, the amount adsorbed, if we express in terms of milligrams per gram, that's if there is no term something related to volume of your solution. So we need to calculate this value. So in the lab we can calculate this value, say like milligrams per gram, and if you do this experiment at industrial scale reactor, you say like a 10,000 liter reactor, and since this unit is independent of your volume, you will get exactly the same answer, milligrams per gram. So that's the point of multiplying this value, V divided by M. So this value we cancel our volume, and this one we cancel our mass value. Yeah? So that's the so imagine if you do the experiment with say some other mass of your adsorbent, still we are getting our normalized value. So try to that is independent of the mass or the volume that we use. So I hope I didn't confuse you with all these terminologies. So the purpose of expressing in terms of milligram per gram is to is to is to get some number that I am going to get even if I'm going to repeat the same process in an industrial scale reactor. So we do this type of experiment in the lab. For example, like I have a protein in my lab, and in the solution, or some industrial guy comes to you and tells to you like, I need to recover that protein. I don't know which adsorbent I have to use. And at the moment I am dealing with say like 2000 liters of my solution fermentation broth. So you don't have to ask 2000 liter of that solution. All you can do is like you can do 8 different experiments, say like 25 ml 25 ml 25 ml, and add activated carbon. Do this experiment, calculate the milligrams per gram in each experiment, and then it's going to be exactly the same if you're going to perform the same experiment in the reactor, yeah, in the industrial scale reactor. So and you can try with another adsorbent, say like a silica based material, and then still you can calculate how much mass you adsorb onto the surface of your other material. And if you're going to repeat the same experiment in the industries, then you are going to get the same result. Yeah, so that's the purpose of converting the amount adsorbed in terms of milligrams per gram. We can be okay. C naught minus C. This also give some information about how much milligrams of your butyric acid moved to the solid side, but still we have some unit, say milligrams of per liter. Yeah? So and we have to neglect this. We have to try to remove this unit from the final value. So milligram per gram, this is more like a normalized factor or normalized values. So if we do it in 25 ml, 50 ml, 1000 ml, or 1000 liters, or 10,000 liters, if you do the same experiment, you will get the same amount of value, milligrams per gram. Yeah, so that's the beauty of expressing the amount adsorbed in terms of milligrams per gram. So I hope you all understand. Adsorption is one of the widely used technique in pharmaceutical industries. Yeah, so that's why I know you might have studied this already, but still you have to. It's okay to cover this topic before going into chromatography. And anyway, this is also part of your subject. And then in this lecture I'm going to, I know you all know what is Langmuir isotherm. I'm 100% sure you must have studied all those things in physical chemistry or even in general chemistry. I'm not sure what you studied in the first and second year, but so in this model we can try to learn a bit new in the liquid phase adsorption. Probably you might have not studied before. I will try to show you how to or maybe I will show you some graphical method that allows you to design or deal with the adsorption data. So at least you will learn something new out of this module. So why we calculated QE? So let's come back to this table. So we did the experiment starting from different initial concentration. This is our final equilibrium concentration. So we can calculate this QE values. So QE values, all we need to calculate is something like, I will calculate for the first experiment. So it will be 0.1 minus 0.002. So QE is the amount adsorbed per gram of your adsorbent material. So that's the formula, C0 minus CE, V by M. So 0.1 minus 0.002, we are expressing concentration in grams per liter. So grams per liter multiplied by 0.025 liters, that's the liter of our solution, divided by how much mass we added, 0.5 grams. So liter get cancelled. So you will get a value of 0.004. So here you will get 0.085. We already calculated this one, 0.1395, 0.19, 0.2585, and then 0.2865. So if you plot CE versus QE, you will get something like that. So this is called adsorption equilibrium data. So when we talked about liquid-liquid extraction, we know that is something that exists in equilibrium between a raffinate and extract phase. So it's the same. There is some solute which is in equilibrium with your solution side and your solid side. Sorry, x-axis is your CE, y-axis is amount adsorbed expressed in terms of grams per gram, CE expressed in terms of grams per liter. So what is this one? So if your CE, say this is say 0.6 grams per liter, this is in equilibrium with your solid. Say if this is say like 0.5 grams per gram. So these two values are in equilibrium with each other, and you have a relation, something like that. So typically people use something called as a Langmuir isotherm to describe the relationship between QE and CE, or to describe the equilibrium concentration of your solute in the solution side to the solid side. So QE equal to QM KL CE 1 plus KL CE. I'm sure you studied these things already. I'm not going to explain too much about this one, so I'll just quickly say what is this. So this is your experimentally measurable value CE. This is something once we perform the experiment we can calculate. This is calculated value. We can measure this experimentally based on mass balance, and CE we can measure experimentally. So QM and KL are constants, or if you want we can call them as theoretical constants. So QM is something called as maximum adsorption capacity. So this number QM is a constant, but it will tell you how much 1 gram of your material can uptake, the maximum theoretical limit. If your QM value is 0.6 grams per gram, which means 1 gram of your adsorbent can adsorb a maximum of up to 0.6 grams. So it's a theoretical value. Obviously it can deviate from real experimental value. So that's the meaning of that. KL is something like a binding affinity. So its scale is something called as a binding affinity. So if KL value is high, it means like your solute molecules are more strongly adsorbed towards that surface. So imagine you have butyric acid, or say example you have a protein in a solution. You do one experiment and you use an activated carbon, and if your KL value is 0.1, and you do another experiment with a silicon material, and if your KL value is 0.2 grams per liter, so what you can theoretically understand from these two values. So I'm going to save this because I'm a bit afraid my tab might crash, and then I will continue immediately. So imagine we are performing two different experiments. In one we are using activated carbon, in another we are using some silica material. So if your KL value is 0.1, and in this case the calculated KL value is 0.2, so what does this mean is like silica strongly binds the solute. This solute can be anything. It can be protein or acid or any other API molecule, for example paracetamol or antibiotic. anything it can be. I hope you all understand up to this point. So what we do is like if we have CE, if we have CE, QE, you get something like that, and this relation will follow this particular expression QE is equal to QM KL CE 1 plus KL CE. The curve that fits all this line can be represented by this single expression. And normally if we have CE and QE, we will linearize these values. So let's cover that in the next lecture. So this week we are going to finish adsorption within 1 week because it's not a complex process. It's very easy. So I will show you how to calculate QM, how to get KL value. So I'm 100% sure you might have studied already. I don't know, but I will show you quickly. It will take maybe 5 minutes to get these values, less than 5 minutes. I will show you directly on the Excel sheet, and then what we will do is like then we will go for a design calculation. So this is an engineering subject, don't forget that. So whatever we are studying, at the end we are going to do something related to engineering. Yeah? So I said to you in the beginning of this course, in the very first lecture, I said this is a nice opportunity to learn the engineering aspect of different unit operations. In physical chemistry you might have learned some basic stuffs like okay, adsorption is a surface phenomena. I have to deal with solid, one is adsorbent, and another thing I'm going to call it as adsorbate. But here we already touched some concepts of chemical engineering. I already talked about diffusion, I already talked about what's a bulk diffusion, I already talked about the concentration gradient, I already talked about the driving force. So all these words are chemical engineering terminologies. They are not devised by chemists. So these are pure chemical engineering terminologies. And then we also talked a bit about this Langmuir isotherm and so on. I already talked about the theoretical adsorption capacity and the binding affinity and so on. One thing I forgot to mention, let me go back. So I know you all might know this QM is equal to KLCE plus 1 plus KLCE. I said to you these two are constant, QM and KL. So what's units? Units of the constants. So without units, no expression have some meaning. Yeah? So everything will become meaningless. So if you express QE in terms of grams per gram, your QM will be in terms of grams per gram. So they both have same units. So if your QE values is in terms of grams per gram, your QM will be whatever the value you calculate for QM, that will be expressed in terms of grams per gram. And if you express CE in terms of grams per liter, your KL value will be exactly inverse, liter per gram. And imagine if you express QE in terms of milligrams per gram, your QM value, the unit will be automatically milligram per gram. And if you express, say for example, CE in terms of milligrams per liter, automatically the unit for KL will become liters per milligram. So keep these things in your mind. So I need to check a few things in my note, checking it quickly. Probably I think I can cover a bit more in this lecture itself. So how to get these QM KL values. So how to get Langmuir isotherm parameters. You know probably you might have done this in physical chemistry. So I will quickly show you how to do this, and in the next lecture I will show how to make use of these Langmuir isotherm parameters to perform a chemical engineering calculation. Yeah, something like you are exploiting those calculated values to design something a bit more. And then I will also cover a graphical method that's going to be a bit tricky. So in your exam you might get a lot of problems where you need to use again and again graph papers, and for the theoretical part you will answer some multiple choice questions, one mark questions, and so on. Yeah, it will be very time intensive exam. So how to get this Langmuir isotherm parameters? So all we need is to linearize this expression. Qm KLCE 1 plus KLCE. So let's take inverse of this one. I'm just taking inverse of equation 1 KLCE. So now we can expand that equation. 1 divided by Qm KLCE plus KLCE divided by Qm KLCE. So and then we can multiply by CE on both sides. CE on both sides of the expression. So CE by QE will be equal to CE by QM KL CE plus KL CE divided by QM KL CE, another CE. So CE and CE get cancelled, CE get cancelled. So you will end up with a linear expression CE by QE that's equal to 1 by KL QM plus KL get cancelled, CE by QM. So let's call this as equation 2. This is look like a linear expression. Y is equal to x plus C plus mx. So what is this? Where you all know this equation. You have y, x and y, and then this is your intercept, we call it as c. This is your slope, we call it as m. So y equal to mx plus c. That will be your straight line which is on this plot. I hope you all know this simple linear regression technique. You must have studied this before. So we have some expressions. So CE by QE is equal to CE by QM plus 1 plus KL QM. So this is your C value, and then so CE by QM we can write it like 1 by QM multiplied by CE. So 1 by QM is nothing but your slope m. So if you plot CE by QE versus CE, you will get some linear line. This will be your fitted data. So just draw a line, and whatever the intercept, so that will be equal to, your intercept will be equal to 1 by KL QM, and then the slope value will be equal to 1 by QM. So therefore QM will be equal to 1 by slope, and KL value will be equal to intercept multiplied by QM, or this will be equal to intercept multiplied by 1 by slope. So that will be your KL value. So that's how you get your Langmuir constant. So if you have CE, if you have QE, you take CE by QE and then you plot, and then you use this expression. So you plot them, you take the intercept, and then you take the slope. From these two values you can calculate your QM value. QM value will be nothing but 1 by slope, and then your KL will be nothing but KL will be equal to intercept divided by slope. I think I didn't do any mistake. KL let me check one more time. So intercept is 1 by KL QM. So KL will be equal to 1 by QM into intercept. Yes, indeed I did a mistake. Let's try this one. So QM is equal to 1 by slope, that's correct, and intercept that is equal to 1 by KL QM, 1 by KL QM. So KL will be equal to 1 by QM multiplied by intercept. Yeah, so that's how you get your KL value. I hope you all follow up to this point. So I'm going to stop recording the video now. So in the next lecture we will deal with a graphical method. So we will get something like CE and QE. We'll get some curve like that, and then I'm going to draw something called as operating line, like different lines, in order to get some useful numbers. So that's what we are going to cover in the next lecture. So we just revised everything that we need to know about adsorption. So with that knowledge we can go on to the, when we are going to talk about chromatography, I will tell, okay, something is diffusing something is diffusing, and something is desorbing, something is adsorbing. So I will use these terminologies when we are going to talk about chromatography. And for adsorption itself is a very important unit operation in a pharmaceutical industry. So we will solve one or two problems, something related to pharmaceutical industry using adsorption technique, and then I will show you one design or graphical procedure, yeah, that you may not find it in your physical chemistry textbook. This is a pure engineering calculation that we are going to do it in the next lecture. So thanks for listening. And then we are in the and this week in the tutorial I will try to solve one problem related to nucleation. Yeah, so we need to solve few problems in crystallization. So this week I will try to do it, and then this week I will also finish the topic of adsorption, and next week we will go to column chromatography. That one also, like in chromatography we are going to see how the principle works. We are going to deal only with the liquid chromatography, and we're going to learn some terminologies. So both chemists and chemical engineers, they use this technique often. So and then you will try to know some theoretical terminologies in chromatography. They might be bit tough as well. So and we will solve some problems in chromatography as well. So I think it's enough for the moment, I think. So thanks for listening.